Okay. So we're going back to the automatic differentiation topic. So our speaker today is William Mose. So he's going to talk about his recent work on the Enzyme framework. So please go ahead. Thank you.
Hello. Hi, everyone. First of all, can you see the... OK, great. Hi, as mentioned, I'm William Moses, and today I'm going to be talking to you guys a little bit about enabling generic parallel automatic differentiation in a very fast way within the enzyme compiler framework. So first of all, this work is not just the work of myself, but a much larger team of folks across Argonne, MIT, and Lawrence Livermore. So to start with, we're going to do a quick review of everyone's favorite subject from either high school or college, AP Calculus. So once again, derivatives are really useful tools for being able to compute the rate of change of a given function's output with respect to its input. It also turns out that these derivatives and other sorts of generalizations like gradients and Jacobians and the like are very widely used across science. In machine learning, some examples of this include the backpropagation algorithm for training neural networks, or Bayesian inference. In scientific computing, this is very common in both modeling and other forms of simulation. What turns out to be really neat is that you can actually generate these derivatives of an arbitrary program automatically. So as an example here on the left, we have this ReLU3 function, which computes, as the name would specify, the ReLU of x cubed. And similarly, we can do a code transformation that generates on the right a separate program that now computes the derivative of that ReLU3 function. Now, unlike other approaches that tend to be numeric for trying to approximate the derivative, this automatic differentiation approach is actually able to have a couple of really nice benefits. Namely, it can, as an example, compute the derivative of all of the inputs in a single sweep. And moreover, it can do so without having any approximation error or epsilons from roundoff. So let's see how an example of this actually works in practice. So once again, I've got that same ReLU3 function on the left. I've actually got this thing on the bottom left as well, saying how you could use it in a hypothetical tool called Enzyme. And what actually ends up happening is it takes the source code there on the left and compiles it down to the LLVM representation. And here we see a very similar sort of structure where we have that same conditional branch. We have the optional computation of the POW3, and finally the value that we go ahead and return. The first part of this algorithm goes ahead and for every one of these values and instructions in the original program does an analysis called activity analysis, which computes which ones actually contribute to the derivative itself. In this case, the values that actually matter include the input argument x, the call to POW, as well as the actual value that's returned. Then for all of these individual values that, again, actually contribute to the derivative, Enzyme will go ahead and allocate in zero what's referred to as shadow memory, or in other words, the location in memory where that derivative is going to be stored. Then for all of the individual instructions inside of the original program, Enzyme generates the corresponding what's referred to as adjoint instruction for propagating that derivative value. In particular, you can see here that the what's referred to as the reverse pass mirrors the original code. So specifically, computing the derivative in some sense runs the program backwards. As a particular example of what's happening here as one of these adjoints, we have the instruction POW of x comma 3, and the corresponding derivative for that is to propagate the value 3 times x squared. We can, of course, now go ahead and optimize this, and we get something that looks fairly simple. And for ease of everyone, we have at the very bottom here what that would look like in sort of C++ form, and that looks basically identical to what you might have wanted to write by hand. Now, the code that I showed before was inherently serial. There's no nice ability to take advantage of accelerators, GPUs, or other forms of parallelism. And specifically, inside of the HPE landscape today, any sort of large-scale learning, any large-scale simulations really needs to be able to leverage the multiple forms of parallelism that exist in both these multi-core chips, distributed clusters, as well as accelerators. Now, while there are some parallel AD frameworks, all of these tend to rely on a similar sort of structure, namely that they specifically only work on an individual language and an individual form of parallelism. As an example, on the bottom left, there's a tool for differentiating C++ code that uses MPI. There's a completely different tool for differentiating C++ code that uses OpenMP. And again, there's a completely separate tool that you need to use if you want to differentiate CUDA code inside of Julia. This means that if you ever want to combine multiple parallel frameworks together, again, similar to how we try to build these large-scale applications today, it becomes quite difficult or sometimes even impossible. Moreover, even when these tools exist, they tend to be relatively hard to use. As an example, inside of one of these MPI-style frameworks, I have this sample little code snippet on the right. If I wanted to now enable it to work inside of an automatic differentiation context, I have to go find all my calls to an MPI send, rewrite them to use now this AD-specific MPI send, that in particular, now, instead of passing in just a regular double, I have to pass in now a AD-specific double, as well as also passing in an additional buffer. This means that if you want to go and apply automatic differentiation to a big code base, you actually have to do some fairly invasive rewriting. Moreover, as we see from the diagram on the bottom left, all of these types of transformations tend to be applied at the source level, preventing any optimizations from being able to be applied first. Now, this actually comes with a bunch of challenges. So, ignorant of which particular form of parallelism you like, the parallel AD algorithm in general works in a similar sort of way. Suppose I have this code here on the left, which computes a parallel for loop and sets all indices of an array to be the same value. This is referred to as a concurrent read or a read race, and it's perfectly safe because we're going to get the same value no matter who or which thread executes first. Now, the corresponding derivative of the read instruction is actually to do a separate write instruction, meaning if I were now to do the sort of naive rewriting to generate the parallel derivative code, now I have a write race, which means multiple threads could try to write to that same location at the same time, meaning that I now have non-deterministic and potentially completely incorrect results. Now, there are ways that people have gotten around this, and they typically rely on basically going down to atomics, which of course, while correct, can be relatively slow. And some prior work, in fact, at SC last year showed that if you're able to run both optimizations and analyses first and in the context of GPU differentiation, for example, by identifying which particular memory locations are thread local, and thus you don't need these atomics on top of, can make, in this case, order of magnitudes of difference for speed up. Though, again, that was only in the context of GPU AD, and moreover, only in the context of one language and one parallel framework. And specifically, what I'm here to talk to you today about is how by shifting the differentiation transform to now operate within the compiler, we get a couple of really, really neat benefits. First of all, we can now run optimization first, and we get the advantage of all these analyses. But in particular, we're able to take in arbitrary forms of parallel frameworks, be it MPI, OpenMP, Raja, what have you, as well as multiple languages like C++, Julia, Swift, Fortran, all in one tool, because we're not writing a specific tool for that specific combination. We're writing a generic tool that can take any of these things as an input. Now, in particular, to be able to handle this arbitrary form of parallelism, we needed to come up with a way to efficiently differentiate arbitrary forms of parallelism. In particular, we came up with an algorithm that allows you to efficiently differentiate any DAG-style parallel framework with a corresponding proof of why this should work in practice. We have an interface for being able to detect and identify the different types of parallelism that you might have in whatever your particular parallel framework is, and some novel parallel-specific optimizations that, when applied to these generic forms of parallelism, can collectively improve the performance. Now, I gave a really big claim earlier, which is we can go ahead and differentiate arbitrary forms of parallelism. So to back that up, I'm going to talk to you about how exactly that can happen in practice. So as we saw in the much earlier slide, one of the important parts of this differentiation optimization is to transfer the derivative information from the operands to its users. And in particular, computing the adjoint, or this corresponding propagator, updates the derivative information of the operands that it used. To ensure correctness in an arbitrary sort of scheduling form, all we need to do is make sure that all of the corresponding dependencies, whether serial or parallel, have their derivative updates done before the definition of the derivative of that value. In practice, this effectively looks like reversing the corresponding parallel dependency structure. So here on the right, I might have a spawn off to a bunch of individual tasks that can, for example, come from a parallel 4 or your favorite tasking model. And the corresponding derivative is to now similarly do a spawn, except now it actually inverts the dependency. So now the sink actually becomes a spawn in the parallel reverse pass, and now the spawn actually becomes a sink in the parallel reverse pass. Similar for an MPI style dependency structure, we might have some code here, as shown on the left, that asynchronously sends to a different node, where that different node receives the data, and finally the original node waits for that transfer to be completed. Now, at the bottom, we can see how the corresponding differentiation would go for this. Now, whereas you had a receive before, you have a corresponding send, again, similarly reversing the dependency structure. And again, we have the wait that becomes the, in this case, I receive, and then the I send that becomes now the wait. However, there's a little bit of extra you still need to do once you've gotten this generic parallel algorithm, and that's to take into account that a lot of this data that you might want to use may not necessarily be available at the time you need it for differentiation. So shown as the code here on the right, I might compute the output of some variable equals x squared, and subsequently set x equal to 0. Now, if I wanted to compute the derivative of that output, which is x squared, the corresponding derivative, of course, would be 2 times x, but now I've overwritten x, so if I go ahead and try to compute it, I just get 0 instead of the actual correct intended derivative. Thus, as a consequence, one of these big issues that comes up in practice is differentiation actually requires you to cache or otherwise preserve values from the original program to compute that derivative. And as we saw in this example, anytime you have a value that's overwritten, conservatively requires it to be cached. And instead, if you can prove that that same value is actually available or otherwise create a different mechanism for rematerializing it, you're going to have a significantly faster derivative as well as significantly less memory using derivative as a result. However, a lot of these types of parallel constructs that we've seen have relatively clunky or unknown aliasing and other reading and writing behavior, which means that it's difficult in practice to figure out exactly how to minimize the amount of data. In particular, we remedy this by introducing a couple of novel parallel-specific both analyses and optimizations. As one sort of cute example of this, we have some OpenMP code at the top left. So in particular, we have, again, the output equals the input squared shown at the top left of how you would normally write it within OpenMP. Now, the way the actual runtime and compiler sees this is that the body of that parallel for loop is itself moved into its own separate closure function, now shown at the top left. And in particular, because it has no idea if you might update some of those variables in the inside, it has to pass all of them by reference. So now, inside of that closure, rather than having either out or in directly, I have a pointer to out and in. And because I'm just loading some arbitrary pointer value, I have no idea if these could overlap, and thus I'd have to preserve the value of in explicitly. Now, we can actually do an optimization, which goes ahead and detects that we're not potentially overwriting out or in, since we're only writing doubles, and here we can see that those are both pointers rather than doubles that we're loading. And therefore, by moving this outside the parallel for, or in this case, the parallel structure, we can actually derive the fact that the output and input don't alias, and thus, as a consequence, we don't have to store as much data in memory. Going up a level, so to speak, we took all of these pieces together and we implemented hooks for a variety of different parallel frameworks. In particular, we implemented hooks for OpenMP, we implemented hooks for MPI, we implemented hooks for Julia tasks, and of course, we have the previous support for GPUs, which include both ROCm and CUDA. And because we were able to implement these baseline frameworks, which of course you can add your favorite framework additionally into the mix by registering it, it also means that you automatically have support for any higher level framework built off of it. So as an example, Raja can go ahead and call OpenMP or MPI. MPI.jl itself just calls into OpenMP, and the Julia @parallel macro is just built out of Julia tasks. So any of these higher level things we get for free because it all goes down to the same thing in the compiler. Moreover, we don't just have framework generality, but we also actually have construct generality. So if you have any sort of higher level parallel utility, be it say a reduction, that's automatically handled by the lower level support for generic parallelism. And this includes both manually written as well as syntactic sugar for nice things. So in one of these benchmarks that we actually took a little later on, there is this particular example of a handwritten reduction. So whereas a different framework would have to sort of wrap that in a custom derivative, since otherwise it has no idea what the specific sort of semantics is going on here, because we generically understand how to deal with memory and generically understand how to deal with different forms of threads and parallelism, we get support for it automatically. Now, of course, this doesn't mean that you might not have a couple of optimizations from high-level semantics of these utilities, and you can actually register that. So as an example, we support both a generic OpenMP parallel as well as a generic OpenMP parallel 4, but one of the most common ways to use this is actually to combine these two work sharing and spit off on all threads construct into a parallel 4, which divides it up amongst all threads. So we can have an optimization that has a slightly more efficient way of doing it rather than handling it from these two individual pieces of support. To actually see how we worked in practice, we differentiated 9 distinct versions of 2 high-level applications, both the Lulesh unstructured hydrodynamic solver from Lawrence Livermore, as well as the mini booty application, which contains the computational kernels from a much larger molecular dynamics engine. And particularly, we took these 9 different versions of those 2 different codes, and we took them in a bunch of different parallel frameworks, as well as a bunch of different parallel languages. And we compared the performance against both non-differentiated code, as well as a state-of-the-art AD tool that handled specifically, in this case, MPI code for C++. So you'll only see a graph for the MPI C++1. And of course, all of these benchmarks are fully available, open source, and the URL is there. And since you can start to multiply out the number of combinations that you get of all of these things, especially as you start to examine both strong scaling and weak scaling, I'm only going to give you guys the highlights. If you want to see more details on this, there's a paper that we have here with a full page of graphs if you want to see any more details. So in particular, looking specifically at the strong scaling on the Booty application, which here is actually plot for OpenMP, we have 3 graphs. The one on the left shows what you would get just on generic OpenMP code, not applying any of these parallel optimizations. And what we have here are 3 individual pieces. The blue line going up denotes what the scalability is just for the original or primal or forward pass code. And we can see it actually exhibits perfect scaling on this benchmark as the number of threads increases. However, the gradient itself, it scales a little bit at the beginning, but around like 12 starts to taper off, and we can see it hits sort of a barrier of not being able to continue to scale. And consequently, that red line there, which shows the gradient overhead, or the amount of extra computation necessary to compute both all the derivative of all values as well as the original results, just climbs as you go up in the number of threads. In contrast, now enabling these OpenMP, or rather parallel-specific optimizations, as shown in the middle graph, we actually see that the scalability perfectly follows the forward pass up until about 32 threads, where what actually happened there is we ran this on a machine with 2 individual CPUs. So once you get past that line, there's some extra sort of NUMA effects because you have to communicate across those two CPUs, so you see a little bit of a hiccup before it continues to go scaling. Similarly, if we go look at the Julia tasks themselves, we see that both the forward pass and the gradient scale similarly well. Now, there's a little bit of an extra overhead here on the Julia code compared to the C++ one, just because Julia, as a different language and different implementation, has slightly different code, but still similar overall performance. And the real sort of takeaway here is that those parallel-specific optimizations that I alluded to earlier are really what enable Enzyme to keep the same scalability as the original program. We can also dive into some specifically interesting ones from Lulesh. So here, now we're looking at MPI code. So we have C++ regular MPI, we have Julia MPI, we have MPI that also goes through Raja, and finally we also compare with CodiPack, which is one of those existing state-of-the-art AD tools. And the real sort of takeaway here, and what's plot, is the runtime of both the original code and the derivative, is that for all 3 of those frameworks, C++, Julia, and Raja, you get a relatively flat overhead, which means that the overhead doesn't depend on the number of nodes that you're actually going ahead and running on, whereas the CodiPack one actually has a significant overhead, especially if you have on relatively few nodes, because there's a lot of overhead for CodiPack to do its gradient computation. Now, overall, Enzyme is a bunch of things. Enzyme in particular is a tool for performing both reverse mode and something I didn't talk about here, forward mode automatic differentiation of programs written in LLVM-IR. In the context of this presentation, it enables you to differentiate programs written in a variety of parallel frameworks like OpenMP, MPI, Julia tasks, etc., as well as those written in a variety of languages. Specifically, we also show here that these parallel and AD-specific optimizations are actually crucial for performance, both in terms of the actual runtime, as well as specifically the scalability. And together, these optimizations, alongside the ability to run at a very low level, allow us to generate code for the derivative that keeps a similar scalability to that original non-differentiated code. All the work of Enzyme here, it's open source. We have weekly meetings to discuss various things coming up, and we have mailing lists for users to discuss questions and the like. And we have lots of very fun, exciting, ongoing work for mixed mode, batching, checkpointing, and more. There's a bunch of folks who've contributed in other ways to this work, ranging from just testing it out, finding bugs, reading various iterations of this that we'd like to thank, as well as a number of grant agencies, including several from the Department of Energy, DARPA, as well as the Air Force, who've contributed to funding this work. Thank you so much. Any questions?
Any question for our speaker? Okay.
Thanks for the amazing talk. I had a question about how the auto diff works if you're using something like an MPI send and receive.
Sure.
Is it the case that you talked about re-execution when you compute the gradient? Is it the case that you'll do another MPI send and receive with maybe some intermediate things that you need to do to compute the gradient?
So yes and no. You can actually use optimizations to fuse this together. So if you have pointer values that need to be sent over MPI, you would also duplicate sort of the send in the forward pass. If you're doing, say, a double-based recomputation, you'd have a completely separate accumulation MPI command in the reverse pass. And similarly, once again, you're able to potentially fuse these things together by looking at, especially if you have multiple MPI weights all in a row into a single MPI weight all, and the likes of that.
I have two questions. I can do the first one. So I was wondering what communication patterns there are in these like MPI communication patterns there are in these benchmarks you have. As I'm a bit surprised that the overhead doesn't change given the number of nodes, because a lot of times you want to be overlapping, your communication and computation. And for MPI codes, this is often very well engineered. And so if you start adding in extra communication operations, like you might mess with that balance, which is really important for actually scaling out. So I was wondering if you could speak to that.
Sure. So the one that I showed the graph of, Lulesh, the way that the MPI communication works is it sort of divides it up, this physical space of the simulation into a bunch of individual subpieces and then communicates along the halo. So then the effective additional impact of the MPI calls is, in this case, at most a factor of 2 to also do the corresponding derivative MPI calls. And thus, in terms of the pure scalability itself, it remains similar because we have the same number of calls in this case with potentially a constant factor on top of it. And the sort of like, while you have the communication overhead, you also have the sort of like meat of the work in the middle as well. So again, depending on which version of scalability that you like, you'll see different behaviors. And yeah.
Hi, thank you for the excellent presentation and work. I would like to ask you to comment on the memory overheads and also whether Enzyme supports some, for example, time-space trade-offs, for example, as in Siskin and Perlmutter.
Yeah, so in that regard, there's several individual pieces of work that go into the time-space trade-off. As part of an earlier sort of algorithm that we have implemented internally, we'll look through all of the nodes of the computation graph, mark them as whether or not they can be recomputed or not, as well as which ones absolutely cannot, and which ones can be actually are necessary for the reverse pass. We'll then do a graph cut across it to find what's the minimum number of values that need to be recomputed, and then that goes into sort of one particular part of the heuristic for the recompute versus memory trade-off. In addition to that, we have some higher level rematerialization. So if we can find a particular memory allocation and do all the corresponding stores back into it to get the value that it would have become in the reverse pass, we'll just do that rather than having to cache all those values individually. It's not quite at the level as being equivalent to checkpointing, but we also, with our Argonne Lab collaborators, are working on some higher level routines that will wrap these primitives inside of a generic, say, round-robin checkpointing algorithm.
What was the memory overhead for Lulesh, for example? What was the range of it?
Sure. I don't remember that particular number offhand. I think it was on the order of like 10x if you had a very, very large, like in terms of like MPI and other communications bit. If you had like different amount of like the types of, sorry, not MPI communication, OpenMP communication on that. If you had a smaller amount of that, you'd also end up with a slightly less overhead.
Still have time for further questions? Okay.
So a goal of this work, right, is to support many different parallelism models. So maybe a hard question. I was wondering if you could speak to how this might work for maybe tasking-based programming models, like maybe StarPU or Legion like that, where maybe the computation or the communication is happening very far away in the code from where you define your tasks, and the parallelism is being managed by this like large, mostly inscrutable runtime system from a compiler's point of view.
Yeah, so not necessarily equivalent to Legion, but very similar in sort of the tasking-based framework that you described is actually Julia tasks that we support, where effectively the derivative of a task create is to create itself a derivative task with the corresponding closure and derivative function to be done. Then the corresponding execution of the derivative tasks just similarly runs the derivative task, except now it'll run it in the reverse pass. So whereas previously you'd have the equivalent of the wait for task, that would be the start the derivative task routine in the reverse pass, and analogously the wait or the actually execute the derivative task in the forward pass now becomes the wait for that derivative task in the reverse.
Okay, so the stuff you register can be relatively complicated functions.
Yes. Yeah.
Thanks.
As a follow-up to that last question, so do you have some kind of a mapping, like at the LLVM level, if you see an MPI send, then this is what you're doing, and similarly for Julia tasks, et cetera, and what's the process been for coming up with that mapping per parallel programming model?
Yeah, so effectively we have a variety of different techniques that you can use to register it. First of all, you can just sort of mark a construct as being a parallel for-like construct, and it'll hit all of these sort of parallel for-like pieces because that's a very common one inside of these frameworks. Similarly, if you have a construct that behaves sort of like a task, you can mark that as being task-like and the corresponding routines for how you would handle the parallelism of the task hit into it. If you have something that goes very sort of like esoteric or more complicated, we also have the ability to register arbitrary arbitrary derivatives while also marking it as creating a parallel context for the sake of race resolution and caching. Inside Enzyme itself, we have in the core level definitions for a bunch of the common MPI routines as well as for OpenMP. The Julia stuff actually, because the Julia runtime potentially is necessary for actually being able to generate these additional routines, uses the custom derivative interface to register the parallel Julia task or the parallel for of Julia behaves this way. And similarly, if you want to register your own parallel runtime interface, you would use very similar routines to that. And the question is this a sufficiently common thing that we just put it into core or doesn't need runtime data structures like Julia? And if not, you can then register it at the user level as well.
Thank you.
Great. If we don't have any more questions, so please give a big thank to our speaker one more time.